In this video, I'm going to be introducing waves with some basic concepts and key terms in order to better understand what a wave is and how it behaves. First of all, we're going to answer, what is a wave? So the way I define it is the movement of energy. So not the movement of matter, not a physical thing moving, but energy flowing through space or through a physical object itself. So a lot of times a wave will be defined as a disturbance or a vibration that travels through space or from one point to another. But really that's just referring to the energy that is flowing through different types of matter or flowing through space. So what is the source of all waves? Now there's all different types of waves, from sound waves to water waves to light waves, but all of them have something in common, and that is how the actual wave itself is created. Now if you focus on a sound wave, if you take a look at this tuning fork, if you think about what's happening with the speaker, what's happening with your vocal cords, at the source of every sound wave and the source of every wave that is created, there's a vibration. So based on how these vibrations vary, that will determine what kind of wave is created. Do you have an electron vibrating? Do you have a tuning fork vibrating? Do you have a hand vibrating back and forth with a rope or a slinky? So depending on the size and frequency of the vibration, that's going to create a different type of wave. So moving on, we're going to take a look at the middle section over here, where we have a medium. It's the matter that a wave travels through. And the plural of medium is media. So any type of physical matter that a wave travels through would be considered the medium. So for an ocean wave, the medium would be water. For sound waves, the medium would typically be air. In the example of a slinky wiggling back and forth, the matter would be the slinky itself. So it is whatever matter the wave is traveling through. And if you have multiple, then it's called media instead of a medium. Now, not every wave requires a medium. Most of them do, but some of them definitely do not, which brings us to our next category, mechanical versus electromagnetic. Mechanical is that basic type of wave that does require matter, and if it doesn't have matter or a medium to travel through, then it can't travel at all. For example, sound is a mechanical wave, so if there is no medium present for it to travel through, then you can't hear sound. So if you're in outer space in a vacuum where there's no air, there wouldn't be any sound because there's nothing for the sound to travel through to contact your eardrum and vibrate it and send those signals to your brain for you to hear the sound. On the other hand, an electromagnetic wave does not need a medium. It can travel through a vacuum, it can travel through empty space, it can travel through some media, but it doesn't require a medium to travel. So again, a mechanical wave requires a medium. It absolutely needs some kind of matter to travel through. And an example would be sound. And then an electromagnetic wave is one that doesn't require a medium. An example for this would be any kind of light. So typically, if you're talking about electromagnetic wave, you're really referring to light. For our next section, we have two different types of waves. We have a transverse wave, one that has a... For our next section, we have two different categories of waves again, one that's called a longitudinal wave that doesn't actually wiggle up and down, and we have a transverse wave, the one that does actually have that up and down motion that most people are familiar with. Now, both of these waves have a similar type of velocity. They move from left to right. The direction of their velocity is directed towards the right. Now, the big difference is which way is the wave motion directed. So the way a transverse wave is defined is a wave that has its wave motion perpendicular to the direction of its velocity. Now, if you take a look at my diagram, this is the direction in which the velocity is headed towards the right. And as you can see, its wave motion is directed perpendicular. It's either up or down, creating right angles, causing it to be that perpendicular motion. So it's basically just a wave that moves up and down or back and forth. Unlike a transverse wave, unlike a longitudinal wave that has its wave motion directed parallel to the velocity. For a longitudinal wave, its wave motion is parallel to the velocity, which means that all of its energy and wave motion is directed in the same direction that it's moving. So it's traveling to the right, and then all of its energy is compressing the spring and stretching it out to pass its energy from left to right. So basically all of its wave motion is right along the same direction that the wave is traveling, unlike our transverse wave, which is the one that wiggles up and down. Now, moving on to the anatomy of a wave, there's a few different parts. A couple of them are already labeled on the picture. We have the crest, which is the highest point of the wave. We have the trough, which is the lowest point of the wave. And then at these two parts over here labeled A, both of those are representative of the amplitude. So when showing the amplitude of the wave, it's showing any spot that has a maximum displacement from equilibrium, and then this flat line around the middle would be considered the equilibrium line. So if you're talking about a water wave, this would be where if the water was totally calm and flat, and then the parts where it's moving up and down would be the crests and troughs, and any of the crests and troughs would show the amplitude of the wave because it shows the maximum displacement from the equilibrium position. Now, the final part that we're going to identify is this symbol right here. This is the Greek letter lambda, which represents the wavelength of a wave. And the wavelength is from one specific part of the wave to the next, and it's the measurement of one full cycle. So a cycle is something that repeats itself. So if you take a look here, we have a specific spot in the wave, which is the crest, and then it completes one full cycle until it comes back to the crest again, just like over here where it starts at the trough and then completes a full cycle to the next trough. So it is the length of a wave from one part to the next repeating part of the wave, basically the length of one full cycle. So it doesn't have to be from crest to crest or trough to trough. it could be from this part of the wave that's rising up above the equilibrium line to the next part that's rising up from the equilibrium line. So it could be from any spot as long as it goes over to the next repeating spot in the cycle. All right, so that basically covers it for the basic anatomy of a wave, where the crests are the highest point of the wave, the troughs are the lowest point of the wave, the amplitude shows the energy based on the maximum displacement from the equilibrium line, which could be with the crest or the trough, and then we have the Greek letter lambda, which represents the wavelength, the length of one full cycle, one full wavelength. All right, the last two terms that we're going to introduce are frequency and period. Frequency, very simply put, is the amount of waves created per second. The unit is hertz, which is shown by a capital H and a lowercase z. Okay, so the frequency tells you how frequently the vibrations are being created in order to send a certain amount of waves. So if you say that a person's voice is at 200 hertz, that means it's 200 vibrations per second. For period is the exact inverse of frequency. So frequency is represented by a lowercase f, period is capital T. Okay, so because period is a specific type of time, it's not represented by a lowercase t, it's a capital T. And to put that one pretty simply as well, it's the amount of seconds it takes per each wave to pass. So it's the time for one wave to pass, or the time that it takes for one vibration to be made. Okay, so since these are direct inverses of each other, if you have one, you could actually solve for the other by taking the reciprocal of it. All right, so to sum things up, we have a wave, which is energy that is flowing through matter or through space created by vibrations. And when it does travel through things, it is called a medium, which is media for the plural. And that is any matter that a wave can possibly travel through. If something does require a medium, we call that a mechanical wave, such as sound, which does need something to travel through. And if it doesn't need something to travel through, it'd be considered an electromagnetic wave because it doesn't require a medium, although it can travel through things at times, which is basically all types of light. Now, with all these different categories, we have two more, which is a longitudinal wave and a transverse. To put it simply, a transverse wave is basically a wave that just wiggles up and down, and a longitudinal wave is one that sends energy directly over without any up and down motion. So this one says the wave motion is perpendicular to the velocity, so it moves up and down as the velocity moves left to right, unlike a longitudinal wave where its wave motion is parallel to the velocity. So then the wave motion is a bunch of elongated parts of the slinky and compressed parts of the slinky that allow for the energy to go from left to right, just like the velocity. Now, taking a look at the anatomy of a wave, we have the crests, which are the peaks, and the troughs, which are the lowest points, and the amplitude, which describes any part where it has maximum displacement. And then we also have the wavelength. That's another measurement of its distance from one point to another, as long as it's one complete cycle. So if it's from one part of the wave to the next repeating part of the wave, that would be considered one full wavelength. Now, taking a look at the characteristics of waves, we often take a look at the frequency, which is the amount of waves created per second, which is measured in hertz. And then if you wanted to measure how long it took for each one of those waves to pass, or how long it took for each one to be created, we would call that a capital T period. So I hope that was helpful in helping you understand the basics and some of the key terms of waves. Thank you for watching and listening.